Okay, in this video we're talking about ideal sources, both voltage and current. And to give us some context to discuss it, I'm going to also cover Ohm's Law. Alright, so let's start with the simplest circuit that we can think of, which is our battery circuit. Alright, so we have something connected to the plus terminal of the battery, and we know that there's current that's going to flow. And we're representing something like a light bulb with a resistor. Okay, resistance is measured in ohms. The symbol for ohms is capital omega. All right, so I know the electrons move in the opposite direction of positive charge, so the positive charge is actually going to be going this way. All right, so here's I, and we would say plus, minus, representing that separation of charge, plus, minus, V. Okay, and here's the thing, we can come up with Ohm's Law. Ohm's Law is basically the voltage across the resistor, VR, and it assumes the passive sign convention. Okay, so once I pick the reference current, all right, so I have current move this way. Then if I'm going to use the passive sign convention, I'm locked into plus being on the top and minus being on the bottom, because the passive sign convention means that current is moving in the direction of a voltage drop. Okay, so that's the passive sign convention, and if that's the case, then VR is equal to I times R. All right? Okay, so a couple of things. First of all, we're not going to draw a battery like that every time. We're going to replace that with an ideal source. All right, so there's different forms that you can use. One is parallel plates that look like this. Another form is you see several parallel plates that look like that. Okay, sometimes you just see a circle with a plus and a minus. All those mean the same thing. It's a voltage source. It's an ideal voltage source with a certain constrained value V. Okay, typically when you draw it like this, these are DC sources. If I wanted to draw an AC source, usually you have some mark that indicates it's like a sinusoidal type of voltage, VAC. Okay, so let's get rid of that. That's just sort of an aside. All right. So from here, we're going to connect the rest of our circuit. We put in the resistor. We reference current this way, plus, minus, VR, where this is R. All right. Now, what is the value of VR? Okay, so what we know is that if I wrote a loop, all right, and let's start here and go in this direction around the loop. Okay, we know how to do that. We've done KVL. I have rises on one side and drops on the other. All right, so I have a rise of V is equal to a drop of VR. All right, and then from Ohm's Law with the passive sign convention is I times R. All right, you replace VR with I times R. So capital V is I times R. All right, so what I want you to notice here, let's choose some values. Let's use 10 volts here, and let's use an R value of 1 ohm. If that's the case, what would the current be? All right, so I plug into Ohm's Law, 10 is equal to I times 1. I in this case would be 10, so 10 amps. All right, then if I change the load, what if I change this to 2 amps? Okay, if I change this to 2 amps, I'm going to get a different answer. I'm sorry, if I change this to 2 ohms. In this case, I is equal to V over R. V is fixed at 10. You divide by 2, you get 5 amps. Okay, so you see what's happening here is the voltage source is maintained at a certain level. All right, this is a diagram of an ideal voltage source. So in this case, the battery is supplying the current for a fixed value of voltage. All right, so the current will adjust to fit the laws of physics, all right, and it will turn out to be whatever it needs to be to get the math to work out, to get the equations to work out, okay? So just as one more example, if I put this at 10 volts and I change the resistance to 10 ohms, what does the battery supply in terms of current? The battery supplies 1 amp. So it adjusts to maintain this prescribed voltage and hit the given current. Okay, so that's an ideal voltage source. All right, an ideal current source works much the same way. All right, the symbol for that is usually a circle with an arrow in it. All right, so this has current I, and then if we put this into a series resistance, here is R. What do we have for VR? And what do we have for VS? Okay, I'm gonna move this over here. Okay, VS is the voltage across the current source. All right, let me go back here. What is the current through the voltage source? All right, the current through the voltage source is the same as the current through the resistor. That's how it works with connecting things in a series loop. All right, so the question I'm going to ask now with an ideal current source is what value of voltage is generated. Okay, so let's make the value of I be 2 amps. Okay, and let's start with an R value of 1 ohm, just like we did before. All right, so if I do a KVL equation, just like I did before, write a loop equation around this loop. Okay, I get a rise of VS equal to the drop of VR. Okay, but VR, according to Ohm's law, is I. I is forced into that branch current by the current source. Okay, so that's going to be 2 amps times R. Okay, so in this case, VS would be 2 volts. All right, so the current is fixed and the voltage across the current source will adjust to meet the laws of physics. All right, so if I change the R value, if I change R to 2 ohms, for example, what is VS going to be? VS is going to be VR, and VR is the current times the resistance. Okay, so 2 times 2 would be 4 volts. So if you change the load, all right, the current stays fixed because it's an ideal current source. All right, and VS adjusts to meet the laws of physics. Okay, so that's the idea. We've covered essentially Ohm's law and ideal sources. One of the mistakes that people tend to make is assuming that for an ideal voltage source, a lot of people just assume that voltage is 0. It's never 0 unless it's not providing any power to the circuit. Okay, so it would be very unusual for the circuit to work out to where the voltage across a current source is 0. All right, it could theoretically happen, but in general, it doesn't. All right, so you might think, well, I can go to an electronics store and I can buy a battery. Can I go to an electronics store and buy a current source? Well, it turns out no. All right, we typically don't buy current sources, but if you're an electrical and computer engineer, you move far enough up in the curriculum and you find out, oh, you can build something that acts like or close to an ideal current source. All right, so along the way, we've talked about ideal sources. It turns out, an ideal source is just that, it's ideal. All right, if you really looked at a battery, okay, so let's say we had a battery here and we were connecting loads across the battery, okay, and this is a bad idea to do. Take the battery and completely short it, okay. If you set the resistance to 0, okay, then what is the current? I is, V equals I times R. So I is equal to V over R. Right? As R goes to 0, the current would head towards infinity. Okay, we know that doesn't really happen with a battery. So what is going on? Well, it turns out the best model for a battery is actually an ideal voltage source. So maybe you have a 1.5 volt battery and then a small amount of resistance. Okay, maybe 10 ohms. It just depends on the battery. Okay, and then you can connect an R. All right. Typically, the R's we would connect are much bigger than the internal resistance of the battery. Okay, and so there's not much voltage drop across the battery compared to R. So, for example, if R were 1,000 ohms, all right, we could start working a circuit problem. All right, here's the current I. All right, we can write KVL equations starting here and working my way around. Okay, I have a rise of 1.5. All right, and then remember I use the passive sign convention for resistors. So that would mean plus minus V10 ohms. Okay, so I'd have a drop of V10 and then plus minus V1000. So it's another drop of across the 1,000 ohm resistor. And then I use Ohm's Law. I times 10 plus I times 1,000. Okay. All right, I could solve for I. I would be 1.5 divided by, you pull out the I, you'd get 1,010. Okay, so this would be really close to what we would get if we just ignored the 10 ohm resistance of the battery. If we just assumed it was 0, okay, I would get 1.5 over 1,000, which is pretty close to the same answer. These are approximately equal. All right, so most of the time we will neglect the internal resistance of a battery, okay, but it is true that if you short the terminals of a battery, you'll get a lot of current, but it's limited by the internal resistance of the battery. So, oh, by the way, it turns out it's a bad idea to carry batteries in your pocket. You have keys and things, and it's possible to short the battery inadvertently with the keys. I know this firsthand because I've had it happen to me where I'm carrying a battery in my pocket, it shorts out and gets hot really quickly. All right, so there's some things about ideal sources that you should know. We'll keep moving forward and you'll use ideal sources for the rest of this chapter on circuits.